So today we will talk about the beam shear stress for cylindrical members, like this kind of cylindrical members. The maximum shear stress Fe for cylindrical member is given by the equation. This is the cylindrical force. Here it's a F or V, both are same only. F or V, that's not an issue. That's a cylindrical shear force, and 0.5 times A. A is the cross-sectional. Here you can see A is the cross-sectional area of the tubular. So tau equal to 0 at the top and bottom also, and it is maximum at this neutral axis. The value is tau equal to 2f by A. That's a maximum shear stress distribution. So shear stress is distributed like a parabolic, and with a 0 at the top and bottom, and maximum at the neutral axis. The neutral axis value is 2 times force divided by cross-sectional area. This is 2 times force divided by cross-sectional area. That's the maximum shear stress. That's why force tau, it becomes F divided by 0.5 times area, cross-sectional area. So F is a maximum shear stress. V is the transverse shear force, A is the cross-sectional area. To ensure the structural integrity of the beam, the allowable bending stress should not exceed a certain limit. So you can understand one thing: to ensure the structural integrity, if the structure has to be integral, like structural integrity we need to maintain, means we need to ensure that the allowable stress is 0.4 times yield value. That means 40% of yield value. You know the stress strain curve, it goes like this, right? The stress strain curve, and this is the strain and this is the stress. We know the yield value Fy. So 40% of this value is the allowable shear stress. You can see 0.4 times Fy. That's allowable shear stress. So the actual shear stress should be limited to this allowable shear stress. Allowable shear stress almost 40% of yield value. So the allowable beam shear stress should not exceed a certain limit. This allowable shear stress is determined based on the yield stress of the material, and is calculated as follows. Fe is the allowable shear stress. Fy is the yield shear stress of the material. Yield stress of the material. It's essential that the maximum shear stress Fe, maximum shear stress Fe, does not exceed the allowable shear stress to ensure the beam structural safety. So we can have a numerical example. Transverse shear force, we can see 100 Newton, and cross-sectional area 4000 meters square. It's a tubular yield value 350. First thing is we need to calculate the maximum beam shear stress. That's maximum beam shear stress. We know it's a V by 0.5 times A, 50% of cross-sectional area. So once we plug in the value, we get the actual shear stress. Calculate the maximum beam shear stress. Maximum beam shear stress, that's what it's calculated. That's the maximum this value. Then step 2 is calculate the allowable beam shear stress. That depends on the yield value of the material, 40% of yield value. That becomes 140 MPa. So allowable is this much. So actual maximum shear stress is this much. It's very less compared to the allowable. So here we can see that perform the unity check ratio. We can see unity check ratio is calculated by the maximum, dividing the maximum stress by allowable shear stress. That's calculated by dividing the maximum shear stress by allowable shear stress. So this is the unity check ratio. Once substitute the values, you can get the ratio is less than 1.00. It's like unity check is which is less than 1.0. Conclusion: since unity check is less than 1, the beam is safe with respect to shear stress, meaning the shear stress is well within the allowable limit. This is the maximum shear stress, this is allowable shear stress, this is the unity check ratio which is less than 1, indicating the beam is safe. And this comprehensive example shows how to calculate the shear stress, maximum shear stress, and assess the shear stress for the beam using unity check ratio. So here you can see Dr. Smith is telling, good morning everyone. Today we are going to discuss beam shear stress, which is the key concept in designing structure much like beams. Let's start with the basic formula. The maximum shear stress for cylindrical members, you have to note that this is for cylindrical members, is given by V divided by 0.5 A. V is the transverse shear force and A is the cross-sectional area. But before we get into details, do any of you have any questions about shear stress? Do any of you have any questions about shear stress? Dr. Smith, understand the shear stress is how the material resists sliding when a force is applied. But what exactly does the formula represent? What is the meaning of each part? Good question, Alice. In the formula Fe equal to V by 0.5, V represent the shear force acts across the beam. It's like the force pushing the beam sideways, causing it to bend. The A is the cross-sectional area of the beam, which tells us how much the material is available. The cross-sectional area, how much area is available? How much area is available to resist the force? The cross-sectional area tells us how much area is available to resist the force. The 0.5 factor comes from simplifying the shear stress distribution across the section. Let me give you an example to make this clearer. Suppose we have the beam when a transverse shear force 100 megaton and the cross-sectional area is 4000 meters square. The maximum stress would be F equal to this much value. Wait, so the maximum shear stress is only 0.05 MPa. That seems really low. Shouldn't the shear stress be higher if the force is high? If the force is high, the stress is obviously going to be high. That's a good observation. The shear stress depends on not only the force but also the cross-sectional area. If the beam has a large cross-sectional area, even the high force might result in a relatively low shear stress. So shear stress is function of force as well as cross-sectional area. Even if the force is high and the cross-sectional area is also high, if the beam has a large cross-sectional area, even the high force might result as a relatively low shear stress. That's why it's important to consider dimensions of the beam when calculating the shear stress. That's why it's important to consider the dimensions of the beam while calculating the shear stress. So if I understand correctly, shear stress that resists the sideways force. F is the shear stress that resists the sideways force, but how do we know if the shear stress is safe for the beam or not? How do we know if the shear stress is safe for the beam?